Next, shear stress distribution for different sections. First, consider the rectangular section. Okay, it is the shear stress distribution for rectangular section. Consider a rectangular cross section having width B and depth D. Okay, the distance from neutral axis to the topmost layer is D by 2, and we consider an area EF above the neutral axis at a distance of Y from neutral axis. Okay, the depth of this section is ABEF is the distance from neutral axis to the top section is D by 2, so that D by 2 minus Y, it is the height, and width is B. Okay, next, the area of this element is, we know that formula, tau is equals to F into A into Y bar by BI. We calculated in previous derivation shear stress for any cross section. Okay, for rectangular section, A is equals to the area of this element, that is D by 2 minus Y into B. Okay, next, Y bar is equals to distance from neutral axis to the center of gravity of this area, that is Y plus D by 2 minus Y by 2, that is Y plus of D by 2 minus Y. Okay, by simplifying this equation, that is of Y plus D by 2. Okay, it is the distance of neutral axis to the center of gravity of a area. Next, substituting A bar and Y bar values in shear stress equation, will get, that is tau is equals to F into A into Y bar by BI. It is the equation of shear stress. F into B into F into A into Y bar by BI. A is B into D by 2 minus Y, and Y bar is of Y plus D by 2 by BI. By simplifying this equation, we will get the value of shear stress tau is equals to F by 2I into D square by 4 minus Y square. Okay, it is the shear stress developed in the rectangular section at any point from the neutral axis to the center of gravity of a body, where Y is the distance from neutral axis to the element distance. At top edge, Y is equals to D by 2. Therefore, F is equals to F by 2I D square by 4, where Y is equals to D by 2. Substitute this value, we will get shear stress at top edge is 0. Next, at neutral axis, Y value is 0. Okay, so that what happened, F by 2I D square by 4. Therefore, by simplifying this equation, we will get 1.5 into F by BD. It is the maximum shear stress developed in the depth of the section, that is at neutral axis. Next, average shear stress, that is tau is equals to shear force by area of leaf, that is F by B into D. Area of the section is B into D. Therefore, tau average is equals to F by BD. It is the average shear stress. Okay, from 2 and 3, tau max is equals to 1.5 into tau average. Okay, it can be written as tau max is equals to 1.5 times of tau average. Okay, it is the shear stress distribution across the various sections. Okay, now calculate shear stress distribution for rectangular section. Here, the problem given that a rectangular beam 100 mm wide and 250 mm deep is subjected to a maximum shear force of 50 kilonewton. Okay, for this we need to determine average shear stress, maximum shear stress, and shear stress at a distance of 25 mm about neutral axis. Okay, it is the rectangular beam given that 100 mm wide and total depth of the beam is 250 mm. Okay, distance from neutral axis to the top section is 125 mm. Okay, B is 100 mm, shear force is 50 kilonewtons, and depth of the beam is 250 mm. Okay, first we need to find out average shear stress. Average shear stress, formula for average shear stress is F by BD. F is 50 into 10 cube Next, B is 100 mm, depth is 250. Okay, it is 2 Newton per millimeter square. Next, similarly, we need to calculate tau max. Tau max is 1.5 times of tau average. Okay, 1.5 into tau average is 2. So that 3 Newton per millimeter square. It is the maximum shear stress developed in the rectangular beam. Next, third one, that is maximum shear stress at a distance of 25 mm above the neutral axis. That is y value they given as y value 25 mm. Next, we know that formula. Shear stress tau is equals to F by 2I into d square by 4 minus 5 square. It is the shear stress formula for rectangular cross section. Okay, that is, we know that formula for I, that is BD cube by 12. Okay, by simplifying this equation, we will get the value of I. Substitute I value and D value and Y value in the shear stress equation. We will get the value of shear stress is 2.88 Newton per millimeter square. It is the shear stress distribution in the rectangle beam. Now we need to draw the variation of shear stress, okay, along the length of the beam. At neutral axis, that is maximum, that is 3 Newton per millimeter square, and top surface and bottom surface is 0, and at 25 mm above the neutral axis is 2.88 Newton per millimeter square. It is the shear stress distribution along the thickness depth of the beam. Okay, coming to next problem. Here the problem given that a simply supported wooden beam of span 1.3 meters having a cross section 150 mm wide and 250 mm deep, okay, carries a point load W at the center. The permissible stresses are 7 Newton per millimeter square in bending and 1 Newton per millimeter square in shearing. Okay, we need to calculate safe load W. Here it is the given length, simply supported beam, okay, having 1.3 meters length. It is subject to a point load at midpoint center of the beam W. We need to calculate this value. The cross section of the beam they given that 150 mm and 250 mm depth. Okay, we know that equation m by I equals to sigma by y. Okay, from this equation we can calculate based on the cross section of the beam. We can calculate easily I value and y value and m value. They given sigma. Based on the m we can calculate W. Okay, we know that maximum bending moment, that is W L by 4 when simply supported beam is subject to point load, that is W L by 4. By substituting length value in this equation, we will get maximum bending moment in the simply supported beam, that is 325 into W Newton millimeters. Next, moment of inertia, that is BD cube by 12. Breadth is 150 mm, depth is 250 mm, breadth is 150 and 250. By simplifying this equation, we will get the value of I. Okay, similarly, sigma max they given that 7 Newton per millimeter square, 7 Newton per millimeter square. Substitute all these values in this bending equation, we will get the value of W, that is 33653.8 newtons. Okay, it is the load value. Okay, next, from this we need to calculate safe load W. We calculated safe load. Next, value of W when shear stress considered. Now we calculated load based on the bending stress. Now we need to calculate value of W by considering the shear stress. We know that the value of average shear stress, that is shear force by area. Shear force is W by 2 into by BD. Shear force is at maximum shear force due to simply supported beam subject to point load is W by 2. That is at midpoint the maximum shear force will occur. That is right side of the midpoint, that is W by 2. So that W by 2 into 150 into 250. Okay, it is the average shear stress. Next, we can write tau average is equals to W by 2 into 150 into 250. Next, we know that condition tau max is equals to 1.5 times of tau average. tau max they given that 1 Newton per millimeter square. It is the value of maximum shear stress. Okay, tau max 1 is equals to 1.5 times of tau average, that is W by 2 into 150 into 250. From this equation the value of W is 33653.8. based on the bending stress and shear stress, both values are same. Okay, it is the method for calculating the load when bending stresses and shear stresses are given. Okay.